So the superforce is c to the fourth. So it's like the speed of light to the fourth power divided by big G. Now, Professor Ashtekar is correct in saying, wait, it cannot be fundamental because it doesn't have the H bar in it. But if you think of it, it's really the Planck force. And how does the Planck force come about? It's the Planck energy, which is the Planck mass times c squared, divided by the Planck length, which is what? G H bar divided by c cubed, the whole thing square root off. Yeah, but because it's, but anyway. So if you do that, the H bar drops out. Now, what's really cool about this, the superforce being the Planck force talks directly to general relativity, because if you look at Einstein's field equations, which you very well know, I mean, I could do the whole thing with the Riemannian curvature times the space-time metric, but let's call everything on the left-hand side G sub nu asterisk, because it's got the cosmological constant term in it, and so forth.
Einstein tensor.
Right, exactly, sir. And equals what? It's 8 pi times big G divided by c to the fourth. You see, when you do the dimensional analysis, and that scalar, that 8 pi times big G divided by c to the fourth is multiplied by the stress energy momentum tensor, your T sub nu, right? But when you do the scaling analysis on that, you realize that 1 divided by L squared goes as L divided by E times E divided by L cubed, which is the energy density, the T sub nu. So that scalar constant that acts in the Einstein field equations is representative of a force. And it's really representative of the Planck force. And you got to ask yourself, what's this Planck force, superforce? Call it what you want. Call it the Alexander force. Who knows? Maybe one day you'll be able to use it and prove with experimental data that this thing does exist. I still do believe it exists at Planck scales. But anyway, let me not diverge. I'm just so enthusiastic that finally someone of your great aptitude is engaging that you know, I'm a little bit, so I apologize if I seem too enthusiastic. But okay, so what I'm trying to say is that what is the Planck force doing in the Einstein field equations if it wasn't a bridge between the world of the very small, quantum mechanics, and the world of the very large, general relativity?
Okay. So, I mean, I think, you know, dimensional analysis is always a great path to take when we're trying to understand new things about that the theory may not be saying, right? So scale analysis and dimensional analysis is, I think, a great way to proceed. One question I have, of course, is that no matter what you do with the Einstein field equation, right, you can always, I mean, at the end of the day, right, and a good exercise, just to walk everyone through this. On the left-hand side of the Einstein equation, we have the notion of curvature, or, you know, let's say geometry, is related or equated with, right, energy momentum, right, matter and, you know, and energy. So, you know, typically, I mean, when we, at least bread and butter relativists and cosmologists that I am, we tend to use fields or fluids to discuss that framework. So we have, on the left-hand side, we have the equivalent of a field, in this case, the dynamics of the gravitational field, seen through the lens of curvature. And on the right-hand side, we have like basically fluids or fields, matter fields, right? So, and then, of course, we have matter or fields or fluids, whatever, right? Space-time, and basically the system is nonlinear, and there's what we call back reaction. You know, the matter can curve the geometry, and the curved geometry makes the matter move, and then that in turn, like, you know, back reacts, right? So you have, because the system is nonlinear. All right. Now I can choose to put vacuum energy, or the cosmological constant, on the right-hand side, right? And it appears to behave like a form of matter. Or I could put it on the left-hand side, right? And that actually ends up becoming something that looks like the radius of the set of space, right? So basically, if I have a positive cosmological constant, I have a curved space time now where the radius, and that's the set of space. Now, so if I get rid of if I work in complete vacuum, and I can choose that, I can choose to work in complete vacuum with a cosmological term, right? Is it not the case that this, what you call the superforce, is something that couples to this vacuum energy?
I see what you're saying.
I mean, there's nothing unless you're adding something else to the Einstein field equation. That's what you have to work with. Now you could do that. You could modify Einstein's theory. There are ways to do this. Right? So are you asking are you modifying general relativity, or are you repackaging it in a way to say that some Planckian scale vacuum energy is what you're calling the super? That's
basically the right-hand side drops to zero. Where's your superforce? And what you're left with is a vacuum solution. But what I'm saying is, don't do that, because it's like choosing natural units. If you choose natural units, the whole idea of C equal H bar equal big G equal 1, you get rid of the superforce to begin with, but you're still left with the beauty of Einstein's field equations, namely space-time curvature geometry is mass energy, which is exactly what it couples to. So the physics is still there, but you've taken away some of the physics that's inherent to the strength, to the, what's the word I'm looking for? To the power of the Einstein equations. And the beauty of the Einstein equations is that they can be reformulated. If you leave the C to the fourth divided by big G in there, if you leave the superforce term in there, it takes a whole different nuance, because it basically says on a quantum scale, it's possible that if you think of the left-hand side as a spatio-temporal geometrical structure, then what it says, it's the superforce acting on the spatial temporal geometrical structure that gives rise to matter, to energy density. That's a whole different look, a whole different understanding of what GR has been telling us. It's a new perspective on old physics, not new physics. I cannot stand when people use the idea of new physics. What if it's just a new perspective on old physics? Nothing wrong with old physics. Old physics like good wine, you leave it, it matures. It tastes even better.
Yeah, but if I work in natural units, I mean, I can always feel free to choose what units I want, and I should see the same physics, right?
Agreed. Which that's why. How should I say? The only problem that I see with that is that once you choose to work with natural units, not only do you discard the physics of the superforce, it's no longer there, but you actually discard dimensional scaling analysis. It's no longer dimensionally correct, because then it says 1 divided by L squared goes as E divided by L cubed. Where's the equivalence in that? Do you see what I mean? When you use natural units and get rid of that scalar, all of a sudden it doesn't make dimensional sense anymore. And I understand from a dimensions point of view, maybe dimensions shouldn't matter anyway. But when you translate those dimensions, 1 divided by L squared as being your space-time curvature, so that's your left-hand side, and goes as E divided by L cubed, whoa, it's basically saying, yeah, space-time geometry is like an energy density. Yeah, I understand. But from a dimensional perspective, it's no longer there. It is no longer there. How can 1 divided by L squared be as E divided by L cubed when E is really your MC squared? There's something not right when you use natural units and drop out the superforce. I understand what you mean overall physically.
Well, in that case, E is just M, right? In those units, E is just M, right?
Fine.
Not C squared.
Fine.
Right.
But even then, 1 divided by L squared goes to M divided by L cubed.
Mm-hmm.
Even from, you see what I'm saying? Even from, I mean, okay, say you keep the M, it's still divided by L. Are you saying that a mass divided by a volume goes as 1 divided by L squared? Are you saying that how should I say, a mass density, right? Because that's what M divided by L cubed. A mass density goes as really 1 divided by surface area. You see what I'm saying? It no longer makes physical sense at that point. Once you use the natural units and get rid of the superforce term, the C4 divided by big G. That's all I'm saying.
Yeah, well, I'll have to, for me, I'll have to see. I mean, one of these things I have to see, the.
Would you look at some paper I come up with?
Sure. I think that's fair. That
means a lot.
Fair.
That means a lot. And I would really love to stay in touch with you, not only because we're New York City boys. We basically, I went to Brooklyn Technical High School and you knew DeKalb Avenue, J Street, like the back of your hand. I remember you spoke of a Dr. Kaplan. I think I once met him because he was a good friend of Dr. Arthur Dorson from Brooklyn Tech and also Mr. Lawrence Zimmerman. Those are Amar, they're the ones that brought me up.
You're what we call a homeboy.
Yeah.
Mm-hmm.
But I think you and I have a lot of in our origins, in our background, the way we grew up, and New York City guys. A lot of people thought, at least a lot of people thought I'd amount to nothing. Yeah, you know what I mean. And I mean, look at you, what you've achieved. So hey,
Hey, I did something wrong.
If you enjoyed this toe clipping, then the full video is linked in the description. You should also sign up for Toe Mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core toe community. You'll also receive my top 10 toes. Think of it as the intellectual version of Quentin Tarantino's Obsession.